Okay, so now what we're going to do is, assuming now the function's exponential, so I'm telling you now that this function is in fact exponential, we're going to find a formula for it. Okay, so again, we know that our formula is of the form f of 0, f of x must be c times a to the x. And remember, we saw from above that f of 0 has to be c. Now from the table, again, the table was in the notes, we have that f of 0 is equal to 1. So in this case, we get c must be 1. So right away, that tells us that f of x is a to the x. But now the question is, how do you get a? Well, if you remember, going back to that theorem, we have f of x plus 1 divided by f of x is equal to a. Okay, so let's use x equal to, so if we were to use then, for instance, x equal to 0, we would have f of 0 plus 1 divided by f of 0. That would have to equal to 4 over 1, which is 4. So in particular, combining these two, we get that a must be f of 0 plus 1 over f of 0. But we just showed this is equal to 4, so we get a must be 4, and f of x then must be 4 raised to the x. Okay, so that's this example. Now let's look a little more. So now we're actually going to get to see the graphs of these functions. This is actually drawn through Desmos. Just write that down actually. This is actually drawn through Desmos, which is again a free graphing software. So this is the graph of a to the x here. This is actually when a is equal to 2, but it does display the behavior of the function f of x is a to the x when a is greater than 1. And there are a few things to notice. For one thing, you can see right away that the domain is in fact all numbers. But notice though, from here, the graph gets closer and closer to the x-axis, but it never goes below the x-axis. In other words, the graph's not going to, it never goes below the x-axis, which really tells us a to the x, the function, is positive for all x. So in other words, the range of this is all positive real numbers. In particular, the function here is never equal to 0. Let me just write this here to make it easier. So f of x will never equal 0. There are no x-intercepts, as we just said. It never intersects the x-axis. And the only time it crosses the y-axis is here, which turns out to be 1. And again, we already knew that because if you do f of 0, which is a to the 0, that's 1. And when I say horizontal asymptote, this is basically what I mean. This notation we have seen when I went into the end behavior. And this is saying that the function a to the x, this is going to go to 0 as x goes to minus infinity. In other words, as x gets more and more negative, the function gets closer and closer to 0, but it never reaches there. That's why we say that the x-axis, or y equals 0, is a horizontal asymptote. And there are no vertical asymptotes. And if you don't know what vertical asymptote is, that's okay. But we have a horizontal asymptote. For 4, in terms of this arrow notation, we're basically saying that f of x, which again is a to the x, this is going to go to infinity. It's going to get larger and larger as x gets larger and larger. This function, notice, is also, from the graph, you can see that it's increasing, meaning as you move to the right along the x-axis, the graph goes up, 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 up. It keeps on climbing, so to say. Oh, excuse me, it should not be there. It keeps on going up, so to say. So these are just some very nice properties of the exponential function. Again, here we're assuming that a is greater than 1. When a is less than 1 but positive, well, the function's a little bit different, as we'll see now. Oh, excuse me, before we get to that, if you go back to the graph, these are 3 points that are on the graph. And this is actually very important because this is actually how we graph an exponential function. We'll see some examples of that. We'll see at least one example. But these points are on the graph, though. Again, the first one comes from the fact that a to the 0, which is f of 0, is 1. From the second point, we have that f of 1 is a to the 1, which is a. And from the third point, if you do f of minus 1, well, that's just a to the negative 1. But if you go back to the laws of exponents, this is actually the same as 1 over a to the first, which is 1 divided by a. But this is actually how, choosing these 3 points in particular, when x is 0, x is 1, and negative 1, that's actually how you're able to graph an exponential function when a is positive. It turns out it's going to have the same kind of, let me go back to the graph, it's going to have this kind of behavior here. You know, it's increasing like this. It has a horizontal asymptote. But what number is it actually? But the exact graph, you're going to need these 3 points. Also, the graph here, as you can see, has no breaks in it, no open circles. So this is actually a continuous function. Okay, remember, that's what continuous means. It means you can draw the whole graph without having to lift your pen or pencil off the paper. Okay, good. Now here, this is actually when I actually drew the graph f of x is 1 over 2 to the x. But again, this is the behavior of a to the x when a is positive and less than 1. Okay, so that's good. Okay. So this is actually the graph of y equals a to the x when a is positive but less than 1. So this was a typo, but that's easy to fix. So just like before, the domain is all real numbers. And just like before for when a is greater than 1, the range is all positive real numbers as well. Okay? So again, in either case, the domain is positive. The domain is all real numbers. The range is all positive numbers. Just like before, the function never intersects the x-axis. It gets very close, but it never intersects the x-axis. Numerically, as before, that means the function is never equal to 0. And the only time it crosses the y-axis is at 1, so the only y-intercept is 1. Also, if you were to look at its so-called end behavior, well, here it's a little bit different because as x gets bigger and bigger and bigger, the function gets closer and closer to the x-axis. Numerically, that's telling us this, that as x goes to infinity, the function values get closer and closer to 0. They never actually reach there, though. So in that case, we also say that y equals 0 is a horizontal asymptote. And just like before, there's no vertical asymptote. If you don't know what that means, that's okay. Here, the function's actually decreasing, meaning as you move to the right, as your x increases, the graph actually falls. I mean, it looks like it stops falling, but it actually doesn't. It keeps on falling closer and closer to the x-axis. As before, we have 3 points on the graph, like so. Knowing those 3 points will allow us to actually graph the function as before. And just like before, as we saw, this is continuous on its domain. So in other words, the graph is a single piece. There's no open circles, no breaks in it. You can draw the graph without having to lift your pen or pencil off the paper.